Hello and welcome, ladies and gentlemen, to this year's ELC 2021 talk, Initializing RISC-V, a guided tour for ARM developers, held by Ahmad Fatoum, a colleague of mine, and me, Rouven Czerwinski. I'll start by introducing the both of us, and then we'll start right into the specifics of the RISC-V architecture and what's helpful to know for ARM developers. Let's start with a short take about me. I'm Rouven Czerwinski. I work for Pengutronics, as does Ahmad. You can find me under the nickname eMantor on GitHub, and you can reach me on under the email address on the slide. I do bootloader porting, security consulting and integration, for example, verified boot for IMX platforms, system integration, integrating libraries required for your Linux system, and consulting all around Linux on embedded systems. And so does my colleague Ahmad. He is also doing a lot of kernel porting and kernel drivers, providing driver development for new devices which need integration into the kernel, and pretty much does the same system integration and also consulting all around the Linux embedded stack. Why do we develop for RISC-V? Why should we start investing time into an architecture where we can't even buy Raspberry Pi-like devices yet? RISC-V could very well be the future of embedded devices. We just don't know it yet because we haven't seen devices out in the field which fit our use cases with larger Linux systems and integrations. We also wanted to spare some time for our Barebox bootloader development, so we took the time to enable available RISC-V patches from the community to work on the QEMU virtual platforms. This was the initial step, and the next step was using Barebox for Beagle-V devices, for the Beagle-V beta boards. We also want to be ready for the first real embedded devices, so we want to have Barebox running on the first commercially available RISC-V devices. And it's also very attractive to have RISC-V as a TinyEmu target, because you can do fun in-browser demos with TinyEmu running as a web application within your browser. You can check that out in the link on the slides. Next up is a short RISC-V overview. The base instruction set for RISC-V is very, very simple and consists of mostly integer instructions and system instructions. So if you know ARM assembly, nothing is very surprising to you. You will be right at home. It's also helpful to know that there are 31 general purpose registers. There's also the X0 register, which is constantly 0 to provide a 0 value for your architecture. And then there's the process counter register, which is also special and always points to the currently running instruction. There are also two, so to say, instruction sets for RISC-V. One is 64-bit, that's RV64I, and then there's RV32I, which is 32 bits. And the only difference between the two is that RV64I, the 64-bit instruction set, extends over the 32-bit instruction sets by providing 32-bit instructions. So if you want to run 32-bit you want to target 32-bit register sizes or a 32-bit integer within your 64-bit register, there are directly instructions available for that. There are also different extensions. For example, there's an extension for atomic instructions to have one instruction which atomically exchanges a value. There are extensions for integer multiplication and division. There's an extension for floating point or for double floating point, and for the control and status register. Important to know is that for our Linux targeted use case, we want to have RV64IG, where the G general expands to integer, multiplication, atomics, floating point, double floating point, the control and status register, and the instruction fence instructions. So on most systems which are capable of running Linux, either on 32-bit or 64-bit, you will have all these extensions available, and the kernel does use them. Next up are timers. So the privileged architecture provides a timer register, which is the M cycle if you are in machine mode, or simply a shadow register in the supervisor mode to access the current time. And this access also depends on your mode. So if you have an S mode, where Linux is running in supervisor mode, and then you also have a user mode, you will need to call into machine mode, where usually you will find a supervisor binary interface running called SBI. And you use this supervisor binary interface to get and set the timer from the machine instruction or by directly accessing the shadow register. If you are running in M mode only, you have direct access to the registers, and there's nothing barring you from directly getting your timer value or setting your timer values. This is in contrast to ARM32, where before Cortex-A7 and Newer, which have an architected timer, the timer instructions were specific to your current Cortex processor and needed to be set up separately. On ARM 64-bit, there's also an architected timer, which is always present, so there are pseudo instructions which are used to get the current timer value, and ARM 64 also supports virtualized timers, naturally. Next up is the ABIs. So the RISC-V calling convention, or ABI specification, defines multiple ABIs. However, only the two defaults are really recommended for use. And these are for the 32-bit instruction set, ILPD32D, which means integer, long, pointer are 32 bits, and float is by default always double precision. And for the 64-bit instruction set, it's LP64D, which means that long and pointer are 64-bit, float is also a double, but the integer stays at 32-bit. This is pretty much the same for ARM32-bit, which doesn't have an ABI, and ARM64-bit, which also only supports LP64D under Linux. There were some ILP32-bit extensions, or there was ILP32-bit support available on the Linux kernel mailing list. However, as far as I found out, it hasn't been merged into the main line yet, and I don't know if effort from ARM is still ongoing at this point. Next up are the code models. These two code models available for RISC-V change how global memory is referenced within the code. So there's the MET-low code model, which expects that global symbols are within 2 gigabytes of the linker address, which is mostly 0. And this is implemented by using by loading from the global memory reference and then or loading the global address into a register and then directly loading from the register. And the second code model available for RISC-V is MET-ANY, which expects that your global symbol is within 2 gigabytes of your instruction. So this is a much looser requirement than for the MET-low model, and can be used to access more memory, and makes it far easier to make your binaries run positioned independently, because your entry address is no longer fixed to a specific memory address. And this is implemented by using an AUIPC instruction, which just loads an offset from the current program register and then just loading the address from the register you just programmed. For ARM64, there is a tiny code model, a small code model, and a large code model. However, according to documentation, the tiny code model is not really fully implemented yet and mostly uses the small code model as well. The small code model carries the same, or carries the restriction that global symbols must be within 4 gigabyte of your binary, and the large code model does not impose any restrictions on your code model or how your binary has to look like. And for ARM32, there's just no selection available anywhere there. Let's take a short look at kernel assembly. Since RISC-V or the RISC-V 64-bit instruction set and the 32-bit instruction set carry the same instructions, we can use macros to write assemblies or assembly for both at once. So we can write assembly macros which will just expand to the correct instruction according to the size which has to be loaded into a register. And this is done by using the recs and recload macros within the Linux code. The recs macro is used to store a value at a register offset, and the recl macro is used to load something from a register content. And the size rec macro expands to the register size for your architecture, or in the case of a 32-bit call within a 64-bit instruction set, you can also set it to 4 to force a 32-bit load into a 64-bit register. And this is plainly not possible within ARM32 or RH64, the ARM64 instruction set, because of differing instruction sets and registers. Since ARM32-bit has only 16 general purpose registers available, and ARM64 has 32 general purpose registers available. So you can't simply share the kernel assembly code there unless you impose very, very tight restrictions on the ARM64 instruction set. Next up, I will talk shortly about our development platform. So we have done a development on QEMU or TinyEMU based virtual machines. For I/O to the host system, those are using virt.io to communicate with the host. So consoles or memory images or HDD images are provided by virt.io. Then we are currently experimenting with a LightX VescoRISC FPGA platform on an ACPI X5, which uses a lattice FPGA where open source toolchains are available, which is really nice. And this is a LightX SoC with a lot of components provided by the LightX SoC infrastructure. So LightETH or LightUART are used within that. And then we are using VexRISC cores, which is an open source processor you can download and assemble into your project. And then for some real world available hardware platforms, we're using a StarFive Beagle-V, or still are using, but unfortunately the Beagle-V has been discontinued. A short look into how Barebox on RISC-V looks like for the QEMU platform. We can see on the slide that Barebox provides a so-called Barebox generic second stage, which is really, really useful. In this case, Barebox pretends to be a Linux kernel, so it can be started from any other bootloader which implements parsing of the Linux RISC-V kernel header. And then we are using virt.io for disk.io. So you can see on the right side we have a current Barebox from the master branch. The board is a RISC-V virt.io QEMU platform. It has some flash, which is always present in the virt platforms of QEMU. And then we can see that we are running in S mode because QEMU also provides a supervisor binary interface implementation. And yes, it pretty much works out of the box and can be used to boot a Linux kernel. I was talking about the RISC-V Linux kernel header. We can take a short look into the header we are using for the Barebox generic second image. So on the first line, you're seeing that we are setting up the stack pointer at the current location where our program our program counter is currently pointing at, because the Linux RISC-V header specifies that there has to be a load offset. So the text area will be loaded at a different place and is not loaded directly after this very initial header. Then we have a jump instruction, which jumps to the one label, which is defined further down in the file. So this is used to jump over all of the header and then directly run the Barebox pre-bootloader code, which sets up everything else to run Barebox. Then we have a B-align 8 line, because the next instructions need to be aligned to 8 bytes, because the first two instructions always need to be two 32-bit instructions. Then we have the image load offset. So I was talking about that the header specifies that the text area of the binary has to be loaded at an offset from where it's jumped into. And in this case, this is about 4 megabytes. Then we have the effective image size, which in this case is 2 megabytes. We have a kernel flex value, which is just empty at the moment, and I think it's also empty for the Linux kernel. And we have a version of this RISC-V Linux header, which is defined to be major 0 and minor 2, so 0x2 at the moment. Then we have two reserved fields, which are not used at all at the moment. And then there are two magic fields which have to be present within the RISC-V Linux header to identify it as a RISC-V Linux header. And in this case, the first magic has to be RISC-V, and the second has to be RSC, and then the escaped value 0x5. And at the very end, we have a reserved PE coefficient offset, which is used for EFI. If you want to run EFI payloads, or if you want to have a bootloader which implements the EFI specification, and you want your Linux kernel to be an EFI binary, you have to use that field. Next up is Barebox on Beagle-V. We have the support for that upstream, and it can start Linux just fine. So if you have access to a Beagle-V beta board, please don't hesitate to test out Barebox on the platform. And you can see on the Bootup that, or in this case it's not shown, but first up the Beagle-V also starts an OpenSBI payload as the supervisor binary interface, and then next up jumps into Barebox. So in this case we can also see that the Beagle-V implements S mode and Barebox is running within S mode, but the specification in this case is much higher than it is in the QEMU case, because QEMU only implements an older specification of the SPA binary interface. A short word on RISC-V HART CPU bootup. So if you have a simultaneous multiprocessor system, you will not only have one CPU but multiple CPUs. In RISC-V, those are called hardware threads. This is so that if you, for example, take a look at the x86-64 processors where you have multi-threading, RISC-V, in the RISC-V architecture, we just say that a normal core and a multi-threading core are the same and are just two different hardware threads. And we don't care about whom is able to access resources of another thread or share caches. We just say those are two hardware threads and are done with it, so we don't have to differentiate between different CPUs. Under ARM64, usually bootup of secondary CPU cores is done by calling into the PSCI interface, which is the Power State Coordination interface. And for most architectures I've worked with, this is implemented using the ARM trusted firmware. On ARM 32-bit, there's a lot of varying here. So if you have a platform which is very, very new, like STM32MP1, you have an ARM trusted firmware available as well. Or if you are running Opti, then Opti has to be the one starting cores, and starting cores is only allowed from the secure world. So those also implement the PSCI interface. Or you have direct register access where you can start a core or stop a core. On RISC-V, there are two options. So the very first option as per specification was that all HARTs, all hardware threads, enter Linux, and each HART has its HART ID in the A0 register, and then Linux can identify, okay, I want the core with A0 to be the main core, which does all the boot up until I can start the secondary cores, and the secondary cores will spin until Linux is done with that. But for the newer case where we don't want all the bootloaders to implement the startup of HARTs, because that's very tedious and needs to be done for every bootloader, because they all have to start the HARTs before jumping into Linux, there's the Supervisor Binary Interface HART State Management extension. And this is somewhat similar to the Power State Coordination Interface, where you get function calls into the Supervisor Binary Interface to start a hardware thread or to stop a hardware thread, to get the current status of a hardware thread, or to send it into a low power suspense state where it will wait for an interrupt to wake up again. After this look into the CPU side of things, Ahmed will now start with the peripheral side of things, so have a lot of fun.
So, now we got our RISC-V CPU executing our own code, and we would like to put it to good use. This means we want to interface with the physical world via talking to the peripherals. The way this works on RISC-V systems is by using memory mapped I/O. So just like we access normal system memory, we can issue memory transactions to read and write from peripherals. This works, but having caches in between can complicate this. So we are all on the same page. Let's have a quick primer on cache coherency. So we have two CPUs. Both CPUs have read some region of RAM and have it in their L1 cache. So CPU 1 has modified that region and then flushed it out to RAM. And then CPU 2 wants to access the same region, but it has stale data from before CPU 1 has written its data in its own L1 cache. And then it will access this stale data. Once you have CPU 1 and CPU 2 coordinating with each other, you will have a synchronization nightmare at hand. The way this is usually fixed is by having hardware coherence protocols, which keeps these caches in sync. This is commonplace for D caches on SMP systems, but for I cache it's usually not, because you write it much less often than D cache. But in the context of Barebox, a bootloader, it's normal that you load code. And this code loading happens through the D cache and the execution happens through the I cache. So you will need to do manual cache maintenance. How that looks like is that you normally load your code, for example, by copying it off a network packet when you are doing network boot. Then you will, this copied data, you will flush it out so it reaches a unified cache. And then you will invalidate your own I cache. That means the next time there is some prefetch going on or some instruction execution going on, you will not find these data in the cache. You will have a cache miss and you will get it from the unified cache where you had written your data before. How does that look like for devices? It looks slightly different, because you will not want caches between you and between a device that you are directly accessing. For example, a timer, you will have a bit to configure that the timer should start running. And you will have a memory mapped register where you can read out how many ticks have gone by. And you don't want to read these ticks and always get the same value because it has been cached. So you will want to disable caching for the I/O memory region that is used by the timer and other peripherals. This is done by the hardware implementer. They know, okay, I will map the system memory at this address and I have this region for I/O devices, and they would design their physical memory layout so that part is cached and part is uncached. So no problem there. The problem starts once you have devices that themselves want to access system memory. So the CPU accesses system memory and it goes through the caches, but now you have devices that don't go through the caches. So what are these devices supposed to do so they are aware of modifications done in the CPU local data caches? On x86, what happens is that the devices are aware of the CPU caches. So you have a Cache-Coherent Interconnect. A PCI network controller can access memory normally, and it will be aware about of changes done to the CPU data caches. But on ARM, this depends on the SoC interconnect. So some server grade have cache-coherent interconnects, which means you don't need to do any manual cache maintenance, but most embedded SoCs don't. And on these embedded SoCs, you will do this cache maintenance. You must do this cache maintenance by hand if you want to have devices directly accessing memory. How that looks like, we can see here with this example, we have a processor and we have a network interface that receives packets that we want to process on the processor, and we have system memory which is shared between the processor and the network controller. So the processor will allocate the buffer, and this buffer, it will create a descriptor that describes this buffer. It has its base address, it has its length, it has some bits, control bits that describe to the hardware what to do with this buffer. And then it will take this descriptor, place it in a descriptor ring, which contains many other such descriptors. And the base address of the descriptor ring is written to the network controller. Writing to the network controller happens like we do with a timer. We do a memory mapped I/O access and write that address. Now the network controller is informed about the existence of the descriptor ring. It will take it, it will go through it, and then it will say, oh, there is a descriptor that says I can use it, and there is a buffer. So when it receives a packet, it will directly access system memory and copy its received packet into that buffer. And then the processor will get, for example, an interrupt. It will look through the descriptor ring. It will see, okay, this descriptor is newly arrived. I will take the buffer. And that buffer will propagate through the network stack, where it will read different parts of it and process it appropriately for the protocol. What we see here are three different types of accesses from the CPU. We have the access to the memory mapped I/O. That's the PIO vertical line here. And that one we will want to be uncached. Then we have the access to the buffer. The buffer, after we have received it, many different parts of the network stack will work with this buffer. So we appreciate it being cached. And then we have the descriptor ring, which we use for synchronization with the network controller. And when we set a bit that says, okay, network controller, you can now use this descriptor, we want these changes to be directly propagated to the network controller and the inverse of that. So we want that ring to be coherent. How does Linux deal with it? You have two different types of DMA mappings. We have coherent DMA mappings, which are accessed by the CPU and device in parallel, and we don't need any explicit synchronization, which makes it very good to implement these descriptor rings. Then we have streaming DMA mappings. These are not accessed in parallel, but you will want them to be cached, because once they change ownership, the network controller will use them for a span of time, and then the CPU will use them for a span of time. And just at these synchronization points, the ownership changes, so you will need to account for caches. How that's done is that you have functions, for example, DMA sync for device, that will say, okay, I am the CPU, I have put some stuff into my buffer, now take this buffer and sync it for device. So after that function returns, the address of this buffer can pass to the hardware, and it will access the data I just have written. Keep in mind that this is different from memory barriers. So this ensures visibility, not order, which is what you need memory barriers for. How does that look like on ARM? So you have coherent DMA mappings implemented via the MMU. So if you don't have a Cache-Coherent Interconnect, you will take the page tables and you have bits for the caching attributes. Is this cacheable? Can writes be buffered? And then you can unset these bits to make pages uncached. And if you have direct uncached access to a region of memory on the CPU, and you have the same access uncached but at the device side, you are basically coherent, because there are no caches to keep coherent between them. And so that's the way how you would implement coherent DMA mappings. Then you have streaming DMA mappings, and these you can implement using cache maintenance operations. So once the CPU is done with a memory buffer and it wants to pass it to the hardware, hand off the ownership, what does it do? It cleans its caches. So all data is flushed out to main memory. So when the device accesses main memory, it will find the data the CPU meant to send to it. And then when it's done with the buffer, the CPU will need to invalidate its own caches before reclaiming ownership, because in the meantime there might have been some speculation going on. So you have stale data in the caches, and then once the device has said, okay, I have written to main memory, you can just invalidate, drop your caches, and then read the new data. And there is a whole zoo of barriers on ARM, so you can write optimized code depending on what sort on how strong your ordering should be. How does that look like on RISC-V? So our specification, you can search for coherency in them, and you won't find much, but you will find what I have quoted here. In RISC-V platforms, the use of hardware incoherent regions is discouraged due to software complexity, performance, and energy impacts. How does that translate to practice? Here are 5 different single board computers. They range over an order of magnitude from $100 to $1,000. And if you were to venture a guess which ones of those decided in favor of hardware complexity to save on software complexity, you will probably guess right. Everything north of the $500 decided for cache coherency, and the $100 and $150 boards decided on cache incoherency. So you have actual hardware there that didn't quite follow this discouragement in the specification. And if you want to write software supporting it, you will need to take manual cache maintenance in your hands because the hardware doesn't do it for you. Let's look at these in series. So we have the Allwinner D1. It's based around an CPU from Alibaba, and it's designed with cache incoherency in mind. That means the DMA masters are not cache coherent, and no DMA masters at all are cache coherent, but the page tables have cache attribute bits, and you have instruction for cache maintenance. So it looks like you would have on ARM, but there's a very big difference in that these instructions and these bits are not reflected in any specification. Actually, these bits are even reserved for official use, but not for vendor use. A vendor adhering to the specification should trap if you set these bits to anything else than 0, but they are repurposed for cache attributes bits. Same goes for the vendor-specific instructions. They are vendor-specific. While on ARM, if you have an ARM version 8A, you are guaranteed to have these instructions available and these bits in your page tables, so you can write common code like you do with a multi-platform Linux kernel that uses the same page table structure for many different SoCs. Unfortunately, you can't do that. The Linux support for RISC-V supports multiple boards, also with device trees like you would expect on ARM, but it can't yet support something like the Allwinner D1 or the GH7100 in the next slide, because these do not adhere to some common scheme. But if you are willing to add an abstraction layer in the midst, you can have your coherent DMA by using the MMU to map pages uncached, and your streaming DMA by using these dedicated vendor-specific cache maintenance instructions. For the StarFive GH700, which was in the Beagle-V beta board, for which I ported Barebox to, this one has a C5 U74 CPU, multiple of them. And these CPUs are designed for cache coherent systems. But the MMC and Ethernet controller on this SoC were not cache coherent. But how they approached this was different from the Allwinner D1. They followed a MIPS-like scheme in that they have 2 different SDRAM aliases. They had one alias for cached SDRAM access and one for uncached SDRAM access. So the CPU, depending on whether it needs cached or uncached access, it would either add or subtract given the offset between these physical addresses. What complicated this a bit was that all cache incoherent DMA masters are 32-bit, which is a bit unfortunate because the uncached mapping is above 32-bit and you have no IO MMU to map this around. So what can you do here? What I decided on was, because I just wanted my network controller to work and there was an SRAM that was quite small, a few dozens of kilobytes, But yeah, that was enough for me to do network communication. So I could just network boot another Barebox and so have faster cycles of development. So I decided to have a coherent DMA pool in that small memory. And for later, I intended on reading up on page tables and the MMU support on RISC-V, so I can teach it proper coherent allocation support. Well, I made a version 1, I sent it out, I wrote a bit about it on forum, on the Beagle-V forum, and I was promptly corrected. There is no support for this in the page tables. There is supporting the MMU won't change that, but there is a way around that, in that you just accept that the view of the hardware is fundamentally different than the view of the CPU. So the hardware can only access 32 bits. So it can access that cached alias. But because these caches are only between the CPU and the main memory, even if you access a cached alias from the device side, you will still sidestep the caches and your access will be uncached. So you just need to keep around 2 addresses. One address via the uncached alias, which you use on CPU side, and once you tell you need to reference that address when talking with, for example, the Ethernet controller, you use the other alias, which if you dereferenced it from CPU side, would be cached, but when the device does it, it will be uncached. And that way you can declare your specific coherent DMA pool on top, and the Linux APIs for DMA already support that. Barebox imports them, so as long as your drivers don't do stuff like taking the void pointer and casting it to an unsigned long and passing it to the hardware, you are fine. Just use the CPU pointer for CPU operations and the device pointer for device operations. And for streaming DMA, the L2 cache controller had a register just for flushing, so you could just use that. So now we have seen these 2 hardwares, and they have very different ways of dealing with this cache in coherency. So you will want to abstract this away somehow. And taking a page out of the x86 playbook, that means moving it to firmware, which brings us to privilege modes. So the normal mode we execute in after power on reset is machine mode. We have uninterruptible access to all hardware and we run directly on physical memory. After that, there is a hypervisor mode. Unfortunately, that one is not yet ratified. It's not yet frozen. There was recently an LWN article on that. There are KVM patches, and the specification has been in the finalizing stage for for quite some time now. But, well, it's not yet frozen, and as such, the RISC-V maintainers were a bit hesitant to accept that code yet. Then there is a supervisor mode, where you have virtual memory available where your operating system would run, and then you have the user mode for user space application. And any CPU would mix these modes. So if you have a simple embedded system with no memory protection, you would just have M mode. If you have an embedded system, but user tasks should be somehow isolated with a memory protection unit, you would mix M plus U. And if you have a full-fledged Unix-like operation system with virtual memory, you would have M and S and U. And the way this is designed allows RISC-V to be classically virtualizable. So all instructions that are sensitive to the mode you are running on would trap to elevated privilege mode. That means a hardware implementer could get away with just implementing the exception handling, CSRs in hardware, and then emulate everything in the trap handler. And by the same means, you could even run virtual machines. So S mode could just keep executing code, and once a sensitive instruction is hit, it would get a trap, it would emulate it, for example, by translating via shadow page tables, and then continue execution normally. That works, but it's quite slow because shadow page tables add a lot of overhead, thus the need for hardware virtualization support. Here is an example how that could look like. So you have in Barebox this pre-bootloader that contains some initialization code and it contains a device tree that describes the hardware. And then you have this Barebox proper, which is usually a compressed binary, which you can run just like a multi-platform Linux kernel on a huge number of SoCs. For Barebox, a couple of RISC-V SoCs are supported. Some of them are in S mode, some in M mode, and some of them don't support fence-I. But you need fence-I once you have instruction caches, because you need to invalidate this instruction cache. For example, you have just uncompressed the Barebox, now you want to execute it, but you can't be sure what was in the instruction cache before you uncompressed Barebox there. So you will need to invalidate the instruction cache. Instead of having two Bareboxes, one for architectures for CPUs without fence-I and one for CPUs with fence-I, you can just have a trap handler that supports both. So if fence-I works, everything is well, and if fence-I doesn't work, a trap is raised, and in the trap handler you can make use of this very regular scheme of RISC-V instruction to find out which instruction was the illegal one, and if it's and fence-I could just skip over this instruction, because if you have no instruction cache, fence-I can just be emulated as a no operation. So, well, let's revisit a bit why we talked about privilege modes. It was because we could use it to offload functions into the firmware. So there is an interface for that, and that's a supervisor binary interface. It's a standard for explicitly trapping to firmware so that it can do functions for you. This allows handling platform quirks and offers functions like interprocess interrupts, hard state management, system reset. This sounds like RPSCI, and indeed it has some overlap. In general, you could say SBI is the RISC-V, what the secure monitor calling convention is for ARM, and you have S mode trapping to M mode, which would be exception level 1 trapping to exception level 3 on ARM. And the reference implementation for RISC-V is OpenSBI, and for ARM, it's the ARM trusted firmware A. And like you have these interprocessor interrupt functions, you could also have functions for flushing DMA, so you don't have to encode this vendor-specific stuff into the Linux kernel. You could just ask the firmware for it, and once there is a specification that's frozen, you could use that in Linux. Some people are quite wary of that, to have this layer of firmware that the operating system is just supposed to accept and that you as a user might not be able to change. And they are right in that. Just having an open instruction set architecture doesn't mean you have an open CPU, and certainly doesn't mean that the SoC that results from this will have open gateware or have open documentation. And experience shows that maintaining a product with severely under-documented hardware is very challenging, and it's often not worth the effort in retrospect. So when you are starting with a new project, or you are a hobbyist wanting to invest your time into RISC-V, you should look at it like this. These RISC-V hardware vendors, they benefit terribly, very much from the free and open source software ecosystem that has sprawled around RISC-V. Some of them take active part in this, and these should be rewarded. But the ones that don't provide documentation, for example, to recreate the firmware, you should probably stay clear of those, because they might not be worth the time or the investment if you try to build products using this. What drove this home to me was the GH700 on the Beagle-V beta. So for the beta developers, there was a reference manual of 150 pages available, which is not a lot. So you would expect something of that functionality level to be like 4,000, 5,000 pages of reference manual. And among the stuff missing was the clock tree. And the clock tree is quite fundamental if you want to save power, or if you just started, you want to start the clocks, for example, so you can use the network interface. The vendor provided a downstream fork of U-boot, of SBI, of Linux, Linux Common Clock Framework does a very good job at reflecting such intricate clock trees, and then you could run Linux and dump your clock tree and then learn about the hardware. But clock tree in Linux didn't say much. This was just some fixed clocks. Looking into U-boot, you find 10,000s of line of macro soups. It was directly generated from hardware description. And then you have 1,000 lines of initialization code, which just toggles that reset, enables that clock, then does this, then reparents this, and so on. And you don't really know which ones you need, which ones you don't. Here is an example. This is a MUX. You see you have these defines that reparent the clocks. And looking long enough at this code and at the structure of the bits that are set and that are removed, you will understand that, okay, so these bits are for gating, these bits are for the divider, these bits are for choosing the MUX. And looking into the code, you might glean what are the possible divider values, or which clocks are inherited from which clocks, how you could construct such a clock tree. So in the end, I wrote a script that parses it out, and it generated Common Clock Framework code that looks quite a lot like normal clock framework code in Barebox or in Linux. Someone even ported it to Linux, which I liked very much. Of course, there were missing parts, and they had the comment, well, we will fill this out once we have documentation. And that was my expectation. Okay, we are a beta developer, we don't have yet this stuff available, but come the end of beta, we will get this data. But the Beagle-V Foundation cancelled the GH7100 based Beagle-V, the Beagle Foundation. And well, I am not sure if the vendor will follow up on the promise to provide documentation now that the pressure went away. They provided an Excel table with some information about the clock tree, not nearly enough, and with a very big disclaimer that you may not use this for distribution, for reproduction, copying, using, making derived works. So it goes completely out of the window using that for open source software. And in retrospect, I wouldn't do that again. So expect your vendor to document the hardware if you really want to use it in a product or you want to invest your own time in it. So the most of what we learned during this RISC-V trip, me and Rouven, went into the Barebox port. Barebox did already support the RISC-V before, but we made it more similar to the ARM platform, which is the one that's used most. So if you want to check it out, go to barebox.org. You will see the documentation referenced there and the Git repository. It has a very Linux-like structure. So you have RISC-V for all the ISA support. You have a drivers directory for the drivers. Some of them are used for ARM and for RISC-V. And there are frameworks that enable this to happen portably. Development is done via a mailing list, and there is also an IRC channel where you can in real time chat with other people. There is a matrix bridge, so you could also do that out of your web browser. And what personally got me involved in RISC-V for Barebox was because I am using Barebox not only as a bootloader, but also as some sort of bare metal hardware bring-up toolkit. And that works quite nicely because you have this Unix-like shell with device files, and you can copy from one device file to another. You have an POSIX-like API with file descriptors and so on, which makes it quite nice to directly interact with hardware to test things out, or even just to prepare something before booting Linux. And I wanted to give people a way to try this out without now compiling Barebox or flashing it on a board. So I wanted to use TinyEmo, which is a RISC-V virtual machine that can be compiled to WebAssembly and run in the browser. And yes, that was how I got into RISC-V development. So there is JS Barebox. You can just click on the link and it will open an emulated Barebox for you. And in case you are wondering, Yes, it does run Doom. There is a button for that. If you click it, it will open an HTML canvas element where it will just, by the magic of simple frame buffer, virt.io, and the virt machine for RISC-V, start playing a Doom that was linked against Barebox. So that concludes my talk. I thank you very much for listening, and I will be available here for questions.